And as Jaqueline is setting up, and I want to thank her. She's come from Kansas State. Yep, it says it on there. She, of course, I contacted the K-State people, actually Kansas in general, because they were working with the new frameworks, the new science frameworks. And of course I begged, I said, please, is there anybody that could tell me who could help us out, learn a little bit about the new frameworks that are being shared, and can you do it for free? Can you get yourself here? Can you get yourself back and do it without me having to, because this is all about free, right? But I want to thank her very much for coming here to share with us on the new science frameworks. Thank you very much.
Well, I was up here last year. I collaborated with some folks here at the University of Nebraska at Lincoln. And last year we were up here doing kind of a workshop on climate change. So having found my way out here once, I decided I should see if I could do it twice in a row. And despite all of the work that's being done on US 77, I made it.
Yeah.
Well, thank you for the opportunity to talk. Let me just give you a little background about myself. I'm the director of the Center for Science Education at K-State, and everybody says, oh, that must be me. Well, it's me. I am the center. So it's, pretty lean center, but I spend most of my time working with STEM faculty at the university, adding education components to the research grants that they do. I don't know if you realize it, but every National Science Foundation research grant has to have a broader outcomes component, and so I help them do that broader outcomes component in conjunction with the networks of science teachers in Kansas. And then I also do just a lot of, I would say, grant work, trying to find money to do projects that support K-12 STEM education as well as link faculty to that. And I am a member of the Kansas State team that's reviewing the standards, and actually we just met yesterday. And so I'm kind of fresh from listening to the teachers mostly talk about what they see as challenges with the next generation science standards and what the things that they're really genuinely excited about. In terms of my own background, I started as a high school physics teacher when I finished my bachelor's degree, and then eventually moved into college teaching and sort of on into higher education. But the interesting feature for me was I taught in the early 70s and then later did other things away from science education and came back into science education around the year 2000. And started teaching methods classes and supervising student teachers. What really shocked me was that if I looked at a physics textbook today and compared it to what I taught from when I was a high school teacher, they're niftier these days, and you got all this technology that I didn't have that just makes teaching some of the more complex topics really, really easy. But I didn't think the content had changed at all. I was watching others teach exactly the same content. And it really seems striking that we moved into nanotechnology and medicine has really changed substantially. Biology is into genome mapping and so forth. And yet, at least in the physics world, it's not actually reflected in anything that we do. So as a result, I really have been trying to say, how can we expose kids to more of the frontiers of science, more of the excitement of discovery, and those sorts of things. So when Krista asked me to come up, I decided to just talk about something that's near and dear to my heart, and that is that all of us, you all as teachers, those of you that work in teacher education programs, we work really, really hard to improve the quality of STEM education in the schools as well as get more kids excited. But somehow, there's always the silence from the STEM faculty themselves, and I keep wondering, when is it that they're going to decide that they have to do some changing in terms of what they do at the university? So I've been thinking about this a lot. I even have a couple of plans to share with you at the end, but I think maybe we may be reaching the point where we can get STEM faculty at universities more engaged in this issue and in fact reform some of the teaching that they themselves do at the university. Okay, just a real quick overview in case you haven't seen this. Are you guys a review state? Are you?
No.
Okay. Okay. See, we've been through this 1,000 times, but I wasn't sure. Basically, the framework that was developed by the National Academy of Sciences really sort of laid out the manner in which the current standards are being drafted. And there were sort of three major areas. One, they wanted to move away from science as inquiry and instead embed in the standards what they call science and engineering practices. They said these are things people do if you're a scientist or an engineer. The second one is cross-cutting concepts, big ideas that kind of come across all of the science disciplines and therefore could make what often seems disparate to students a little bit more coherent. The cross-cutting concepts are not particularly new. They were part of the standards adopted in '95. They're just more explicit in this version. And then the last part is the part we're all kind of familiar with within our own discipline, and that's the disciplinary core ideas, where they actually tried to compress the number of core ideas so that teachers would have more time to go into those ideas in more depth. If, I don't know, and if Nebraska does, Kansas used the National Academy standards adopted in '95 or so as the framework for our current standards. And so you see a number of different standards there. Sciences inquiry was one. Then you see the disciplinary content standards, physical science, life science, earth and space science. And then you see a couple of applications, science and technology. That is, how do science and engineers sort of interrelate? Science and environmental and personal perspectives, and then last, nature of science. And when these came out, actually when I came back into the field to start working with methods courses, I was looking at all of this and thinking, well, this is kind of exciting because a philosopher, a member of the philosophy faculty had bugged me in the early '90s about the fact that scientists don't ever talk about the way they do science. And he thought that that was really striking because philosophers do talk about the way science does science. And so he thought that was really an interesting omission. But if you think about it, you were left with these two topics, science's inquiry, nature of science. And I don't know how it is in Nebraska, but in Kansas, our students who go through and get a major in physics or chemistry or geology or biology never sit in a science class where either of those things are discussed. Okay? All they learn about are the concepts, how those concepts are established empirically through experiments or through gathering data, that sort of thing. But nobody ever really, none of the scientists really ever include these topics. And so when I came in and was asked to pick up some methods courses, we had to start doing this because our teachers weren't going to get it from the sciences, so they got it from us through the methods course. And I actually have to say it was kind of fun. My image of science was completely narrowly defined by physics, the particular discipline I'd come through. And I had no idea of the range of types of data, ways of collecting data, ways of validating data that existed across all of the sciences. So it was actually kind of fun for me to do this because I ended up learning as much, if not more, than the students. But we set about integrating a fairly substantial discussion on science's inquiry and nature of science. And I'm from Kansas, so you have to figure that embedded in all of that was helping students figure out how to deal with evolution in the classroom. Because we realized that students were going to be caught in situations dealing with parents who were really angry about the inclusion of evolution. And so we also tried to use nature of science as a vehicle around which to talk about the fact that those with very strong faith-based beliefs about how we all came to be, that faith-based beliefs are another way of knowing, and that science teachers have to teach the scientific way of knowing, and so forth. So, where? We do it in science methods classes. I keep thinking they ought to be doing it in some of the introductory science content courses. Now, nobody listened to me, by the way. I used to say this all the time. Nobody ever listened to me. But when I agreed to join the state team and started looking at these science and engineering practices, these are what are shaping the next generation science standards. And some of them seem kind of okay. Asking questions and defining problems, well, we do a lot of that anyway. Developing and using models, well, I don't know. I never developed a model in either my bachelor's or master's degree in physics. I was given models as ways of explaining why we believe what we believe, but I never actually developed a model. Planning and carrying out investigations, well, we've kind of been doing that with the old standards, so that's not so bad. Analyzing and interpreting data, well, yeah, we've been doing a fair amount of that. Using mathematics and computational thinking, yes. Constructing explanations, designing solutions. Again, I wasn't exposed to those kinds of things coming through physics. Engaging in argument from evidence, I know that's been a growing activity in the schools, but I've got to tell you, nobody ever let me argue from evidence in my physics classrooms. I mean, it just wasn't done. Obtaining, evaluating, and communicating information. So you look at these, and I'm sitting here saying, you know, and the teachers, by the way, yesterday said, as they were looking at the current version of the standards and trying to figure out how they would implement that in the classroom, they just said, well, I can have kids develop models, but I don't know what the criteria of a model is. I don't know how to grade it or assess it. And so the teachers themselves were saying there were elements of these practices that they can agree would be really good ideas, but that they're not really sure they have had the background that they need in order to be able to do that. And I don't know, back in the 90s, there was a really, I think, very substantial research piece done on teachers who were trying to implement the then current California math standards. And they sent researchers into individual classrooms, interviewed the teacher, observed several classes the teacher taught. And as you might expect, there's a lot of variation in terms of how the teachers implemented those standards. But what they finally concluded after, I think it was roughly 20 classrooms that they did the observing in, was they simply said, you know, we need to remember that teachers can't teach in ways they have not first learned. And so when we do standards or when we do reform efforts, the very first thing we have to do is give teachers the opportunity to learn in that manner, because that's in fact what guides their capacity, our capacity to teach. So what are some entry points? How do we deal with this? Well, I went on the offensive a couple of weeks ago. I was at a meeting with Council of Deans for some other purpose. It wasn't even about this. But I had the Dean of Engineering saying, well, you know, we just keep having problems with getting good students in science and engineering at the university level. What can we do to help, or what should we be doing to get more women and more students from populations that are underrepresented in the sciences to get interested in science? And I finally just said, well, you know, I think education has done all of what it can. I said, the barriers these days are not in how well we structure our teacher ed programs. The barriers are not in the current teachers who are only too ready to respond to the standards and teach to them. I said, the real barrier is you all. I said, we aren't going to change any further until the STEM departments at the university decide that they're going to become part of solving the issue. So, content courses, those courses have got to start integrating some of what you all are going to be doing with the new standards, or there's going to be just this huge disconnect between what the kids have experienced in K-12 and what they experience once they get to the university. And Elizabeth did a great job of outlining how you might do this with informal science education. And I have a couple of other suggestions. Once the standards are adopted by Kansas, and I hope they are, but it's not a foregone conclusion. But once they are, I'm going to essentially take the standards to a colloquium for each of the STEM departments in the university. And I'm going to put one of the standards relevant to their discipline up on the screen and say, okay, this is what teachers are going to be doing with kids. You know, are you preparing those teachers in the content courses to be able to do that? And if not, what changes can you make to the content courses that guide what those teachers experience at the university? Another really fun example, I'll let you know how it turns out, is I'm working with one GK-12 project that's NSF funded. GK-12 funds graduate students in STEM fields to go into classrooms and be sort of like a resident scientist for those classrooms. We've had 5-year, we're starting our 5th year of doing this with Junction City High School, which is a school district. And it's been very successful because, first of all, kids get to see a real life scientist, and it actually erases a lot of the stereotypes they have about that. But also, the graduate students talk about the current research that they're doing, so kids get to hear about what's going on at the frontiers of science. And interestingly enough, the teachers tell us that it really reignited their passion for science, but somehow some of that gets lost in the day-to-day work in the classroom, and you think of yourself more as an educator than a scientist. But most people who become science teachers are scientists first in a way. That's where their passion lay. And so the graduate student is able to do that. In addition, the graduate student actually can come up with some creative ways of teaching more challenging content than teachers sort of believe was possible. So we know that the graduate students have an impact on helping teachers sort of redefine what you can do with high school age kids. Well, every summer we do a 2-week summer institute where we bring the new fellows, the new graduate students together with participating teachers and together with the STEM faculty. Sort of talk about the design of the program and what we want to accomplish with it. And every summer, the content people, there's usually one from geology or geography, one from biology, one from physics, one from chemistry. They all do a day or two focused on content knowledge that they think is important to the particular theme they're talking about. Well, the teachers, many of whom do this every year, so they've been to this institute 4 times now, are complaining that we just keep doing the same thing. So the discussion came up with, well, what can we do differently? And I said, I've got an idea. Let's give each of those content specialists a standard that you are all are going to be implementing if Nebraska does. Let's give them one of those standards and have them design a day's worth of instruction around that standard. And everybody bought into it, so next summer, first couple of weeks after Memorial Day, we're going to test this out. And I'm hoping, actually expecting, that this kinds of programs will, this kind of effort will get the faculties to sit up and take notice and recognize really how very different what it is you all do in the schools is to what they're doing at the university level. The other 2 possibilities, if you don't know about them, there's increasing money being given to research experience for undergraduates. So universities can write for and receive grant monies that engage freshman, sophomore level university students in direct research. I have a faculty member in chemistry who's bugging me to see if we can figure out how to do that with high school kids. We haven't yet, but that would be another variation. And RER, I'm sorry, that's a typo, it's RET. There's also research experiences for teachers that are funded projects that universities can get. And so usually you take a research theme and write a proposal to NSF to bring teachers on board, usually for 6 to 8 weeks in the summer, where the teacher actually directly participates and contributes to a research project. So there's other entry points, I think, and again, when the faculty have a chance to work with the teachers and then listen to the teachers talk about what you all experience in the classroom and what you're trying to accomplish, I think that will also have an impact. So that's it. Thank you very much.
Question. How is that GK-12 project funded?
National Science Foundation. Unfortunately, they're ending it. Our project will be one of the last ones out. But it sort of functions a bit like a scholarship program. So NSF specifies that you have to recruit current graduate students. Instead of those students working on a graduate research assistantship or a graduate teaching assistantship, they receive a stipend to be part of this program. It pays $30,000 a year, which is substantially greater than our current teaching assistants and research assistants. Pays for their tuition, and so then they go out into the schools. We require that they be actually in the schools roughly 10 hours a week, and that they do prep work that's equivalent to about 5 to 10 hours. So the time committed is no different than the time you would be involved as a research assistant or as a teaching assistant. And the goal is actually to make these STEM graduate students better communicators. The idea is if you bring these folks into contact with younger students earlier, the graduate students won't get so entrenched in the jargon of the field that they're doing research in, and they'll learn how to talk to a more general audience. And by the way, that does happen. It's really pretty impressive. The other thing it does is create a group of future scientists who are very interested now in K-12 and figuring out how to help. They're comfortable with teachers, they're comfortable in schools. When they are interviewed at the end of their time as a fellow, they talk about wanting to continue those relationships. I think it breaks some of the barriers that Yes.
What would you say would be the single biggest thing that your dean colleagues should do to bridge that gap that you described, that chasm between what disciplinary scientists thinks is what we should be doing in teaching versus what, biology teachers, chemistry teachers, physics teachers are thinking? What's the single biggest thing you would advise them?
Recognize the importance of engaging college level students in more than just memorizing content.
But that's just recognized. I mean, deans really, all they really can do is write checks and hire and fire people. That's really all they can do. So what would you recommend that they do?
I think your workshop idea would be a way. I mean, I had the same discussion at UNK last week. Exactly the same chasm exists out there between their content professors and the School of Education. And some of the chasm is financial as well.
Yes. Although some of those, there are workarounds to some of that. I mean, maybe the best way I could respond is, right now I'm just like the messenger. I'm trying to get people to sit up and take notice. But what was interesting with the very first summer workshop we did with this GK-12 program, the focus of that program is on how scientists use evidence gathered from the past or from distance objects and make inferences based on that. So you're not in a lab where you're getting the data right there, but you are drawing inferences from other data. And it was headed up by a group who did an interdisciplinary course on origins. So physicists who deal with astrophysics or elementary particles, as well as biologists who deal with evolution. And And the very first workshop, they did their lectures, literally. Each one of them had a day, each one of them took their part of that interdisciplinary course and did a stellar lecture, but that's all it was. The teachers really handed good time. And so the next summer, about half of them changed what they were doing to incorporate more active hands-on. So I think it was...
They got some peer review.
Exactly. And suddenly, they weren't the ones in charge anymore. That GK-12 program is run as a collaborative program, and the teachers are as important as the faculty. And that changes the outcomes.
See, scientists are used to peer review.
Yeah.
And on the research end of their life, they hold their work out there and they expect to be criticized. Why don't they do that on the teaching end?
I mean, I got to tell you, I became a teacher because of how dismal physics teaching was at the university. You know, I'm much older than most of you, but in my day, you know, the professor stayed 2 boards ahead of wherever it was I was. And my goal was to get everything written down so that later I could try and see if I could make some sense of it.
Now they go faster with PowerPoints, people have to just click the button and go to the next slide.
So it was real dismal, and that's actually why I got interested in teaching. I think they're better today, at least in the physics community. There's a lot of interest in being better teachers, but that interest is being better lecturers or having better demonstrations. It doesn't get into the active engagement of the students that we're looking for at most levels.
But at UNL, we are starting to see, we had, I think it was January, we had a group of STEM educators in all the different departments. It wasn't just education, it wasn't all science educators like myself. It was scientists who are educators, you know. There were mathematicians that are educators. There were engineers that, you know, because they're starting to see themselves as educators. Sorry to enunciate like that. But they're starting to, there are some, and maybe we're starting to get a mass where it's starting to precipitate out, where people are wanting to make changes because they are interested in the future. And I mean, I can speak for UNL. I can't speak for all the universities, but it is happening, and that's the nice piece. Is it slow? Yes. Thank you very much. Nice.